So in our last presentation, I talked about the idea that general relativity distorts space. Now I'm going to talk about general relativity distorting time, because this is another interesting thing that happens. Remember, light has to travel the shortest distance between 2 points. And so in order for that to work, that would mean that it would take longer to go where the gravity is stronger. So that would imply that time runs at a different rate. It runs slower in the presence of high gravity. And so an example of that would be if you had a tower, and the first floor of the tower, you had like atomic. In fact, this has actually been done using an atomic clock on the first floor of a building and an atomic clock at the top floor of the building. And just like the moving atomic clock was behind one that's sitting stationary with the test of special relativity, the one closer to the ground where the gravity is a little bit stronger is actually running a little behind the one that's higher where the gravity is a little bit weaker. And so that means, well, it means your head ages faster than your feet. But it also means that if you had a light source and it's oscillating with a certain frequency, frequency is related to the period. That period is longer, and so the frequency is less if you're viewing it from farther away. So the light basically can be thought of as being stretched by the gravity, is one way of looking at it. Or another way of looking at it is that the time is running slower here, so the higher frequency is really perceived as a lower frequency further away. And so so that gives you a gravitational redshift. White dwarf stars, very compact, gravity is very strong. Neutron stars, even more compact. Gravity is unbelievably strong near a neutron star. So if you were in orbit around a neutron star, but always the same distance away, but you looked at the neutron star, because it has such enormous gravity, the neutron star would be redshifted. It would be as if it was always going away from you, even though it's always the same distance from you. And that gravitational redshift. Okay, so it's not because it's moving away from you, it's because gravity is so strong, it's slowing time near the presence of it, and so the light being emitted is redshifted. It's shifted to a not shifted because of velocity, but shifted because time is running at a different rate. And so this is a gravitational time dilation. That gravitational time dilation also is related to orbits. For example, the planet Mercury does this sort of spirograph orbit around the sun, shifting a little bit every time around, because when it's closest to the sun, time is running slower than when it's farther away from the sun. And so this sort of shifting here, called the precession of Mercury's orbit, was something that was discovered back in early 1800s, maybe late 1700s, and but definitely by the early 1800s. And astronomers were having a tough time explaining where it came from, because they did not understand anything about gravitational time dilation. And so they were actually suspecting there might be another planet orbiting closer to the sun than Mercury. And so every time there was a solar eclipse in the 1800s, they were searching for this mysterious extra planet. They even named it. They called it Vulcan. And so they were searching for Vulcan every time there was a solar eclipse. They never found Vulcan because that planet's not really there. What was causing the shift in Mercury's orbit had nothing to do with an extra planet. Instead, it had to do with the sun and the gravitational pull of the sun and time dilation due to that. Well, this now starts getting us back into a black hole. So the idea of a black hole is, as something gets more and more compact, you stretch light more and more, you stretch time more and more. So by the time you reach a black hole, you've basically stretched time infinitely and you've stretched light infinitely. The result is that by a separate branch of mathematics, not what we had derived earlier for black holes, but for a separate branch of mathematics, we can now say that therefore you can use general relativity to derive a black hole. And you could say that a black hole is such an object that not only is the escape velocity bigger than the speed of light, but space itself is stretched beyond the breaking point in some sense. It is stretched such a way it's infinitely stretched, and time is stretched infinitely. So in fact, at the Schwarzschild radius, time stops and space is infinitely stretched. So inside the Schwarzschild radius, you back to this deal where it's almost like you're stretched into an imaginary frame. You're stretched beyond the limits. You're back to this dividing by zero thing, or square root of a negative number type thing. So that's what happens. The entire object, if it's bigger than a certain amount, certain size, gravity wins. It shrinks down to a singularity. Anything inside the Schwarzschild radius, which you can calculate, before an earlier lecture, I calculated the Schwarzschild radius, then anything inside that is this space, this region of space where you're stretched beyond the breaking point, beyond the elasticity, you're stretched to the point that if you try to figure out how much you've stretched, you got to divide, you got to multiply by something that is the square root of a negative number. And time inside there is so distorted that to find out how time passes, you're taking the square root of a negative number. So this is all not real. This is all, again, it's orthogonal to the universe. And so these are concepts that are difficult to imagine as to what's happening in there. But basically, you do not have the passage of time in a normal fashion. You do not have the measure of space in a normal fashion. You can't, because of this incredible gravitational stretching and distorting. And so that is what defines your black hole, is if you're inside that Schwarzschild radius, then all this weird stuff happens. Okay, so how big is too big? We're pretty sure that, up to 20, 25 solar masses, you get a really big neutron star. When you get to about 30 solar masses, it begins to the point that it's not real sure what's going to happen. If you get over 50 solar masses, we're pretty sure you get a black hole. So some books say, between 25 and 30 solar masses, if you get bigger than that, you get a black hole. Other books say you have to get bigger than 50 solar masses. It's not exactly clear as to how elastic neutrons are when you get the collapse. So somewhere in the range of 30 to 50 solar masses is probably this delineator. Notice that you still get a supernova. The core shrinks down to a neutron star that's maybe bigger than 3 solar masses. The rest of the star, between 30 and 50 solar masses of that star, still goes into an explosion. So the supernova does not actually consume the entire star. Not the entire star goes into the black hole, only the core does, and the shock of this giant collapse still triggers a supernova, which blows away the rest of the star. So your black hole, that we're describing now, we call a Schwarzschild black hole, is really nothing but a singularity. Everything is shrunk to the singularity. The Schwarzschild radius defines the distance from the singularity at which all the weird stuff happens. Closer than the Schwarzschild radius, then you're basically got space pulled out of the universe. It's no longer the rules of the universe don't apply. Outside the Schwarzschild radius, the rules of the universe apply. All the laws of physics hold, even though they may be slightly modified by general relativity because gravity is really strong out there. Anything that happens inside the Schwarzschild radius can never interact with what's outside the universe. because you'd have to be going faster than light to get away. And besides, time doesn't pass properly in there. Space doesn't pass properly in there. You can't go faster than the speed of light. So that means that any event that happens closer to the Schwarzschild radius will never impact the rest of the universe. Anything that happens outside the Schwarzschild radius, you can see from outside. So we call that distance the event horizon. There's not really anything at the event horizon. It's just this mathematical construct that we calculate this distance at which anything closer than that, any events do not interact with the universe. So all those weird things about things not operating according to time, things not operating according to space, all the non-causality things that happen, they happen inside the event horizon. In fact, it's almost as if time and space go backwards, or not backwards, but reversed. So outside the event horizon, if you sort of force on something, you can move it from place to place, but you have no option about time. You're always going into the future. 10 seconds from now, you'll be 10 seconds in the future. A year from now, you'll be a year into the future. Inside the event horizon, it doesn't work that way. You can exert a force on it and push it into the present or the past, present or the future or the past. On the other hand, you have no option about where you are. You are always going closer to the singularity. And so inside the event horizon, then space and time are almost inverted from one another, though it's mathematically not quite even that simple. So again, this is a very bizarre and weird kind of object that is described mathematically. Okay. In fact, even the term black hole was an attempt to explain to some reporters what was being discussed at a conference, and so the person describing it, Eddington, was so exasperated. He said it's almost like a big black hole in the universe that's separate, pulled away from the rest of the universe. And the reporters, oh yeah, I understand what that means. So black hole was the term. So a type 2 supernova, the merger of two neutron stars, any of these things that puts enough mass together that it collapses beyond that point of 3 solar mass neutron star, that would give you a black hole. And John Wheeler actually was the one that coined the term black hole, and he was the one that came up with this idea that you're trying to explain these things, and the reporters weren't getting it, and so he called it a black. He used it's like a big black hole in the universe, and so that's when the reporters said, "Oh, I understand, black hole," and so that became the term for this object.